There is another form of the trigonometric Fourier series called the compact trigonometric Fourier series. If you recall, previously we had x of t expressed as a sum of, it was a DC component, and then we had an infinite sum of sine and cosine terms. Those sine and cosine terms were all at the same frequencies, so they can be combined into a single sinusoid with amplitude. I'll use Cn to represent the amplitude here. The frequency is the same, so n omega 0 t, but then now we add a phase shift term, theta n. So this form of the Fourier series is usually a little more convenient for electrical engineering work, because we speak of the amplitude at a particular frequency and the phase at a particular frequency. Again, the coefficients here are related to our A0 and B0 coefficients. C0 is still the average value. Cn is an squared plus bn squared. So again, in getting to this form of the Fourier series, we'll typically calculate an and bn using those formulas that were given previously. Theta n then is the inverse tangent of the bn over the an coefficients. Okay. This form of the Fourier series leads to the concept of the Fourier spectrum. And the Fourier spectrum are stem plots of the Cn, plotting the Cn as a function of frequency. These are known as the magnitude spectrum. And then similarly a plot of the theta n values versus, it might be versus either n f0 or n omega 0, but these are known as the amplitude, sometimes also called magnitude, and phase spectra. Spectra is the Latin plural of spectrum of x of t. So let's look at an example now of calculating the Fourier series and sketching the spectra. So this is example 6.1 from your textbook, where we're given the following signal, x of t. So this is my time axis, and here we've got a periodic signal that has this shape, and it has a period of pi. So this shape is going to repeat. This will be 3 pi. This is periodic forever. So it goes off in both the negative for negative infinity as well. And in this interval, we need a mathematical expression for x of t between 0 and pi. So x of t is given as e to the minus t over 2 in the interval for t between 0 and pi. Of course, it repeats periodically after that. Okay. So some information we get from this graph. Our fundamental period is pi seconds. So the fundamental frequency in hertz is 1 over t0, 1 over pi hertz. And then in radians per second, it's 2 pi times f0, so it's 2 radians per second in this case. So here it's going to be a little easier to work with or talk about the harmonic components in radians per second. The fundamental frequency would be 2 radians per second. The second harmonic would be 4 radians per second. The third harmonic, 6 radians per second, and so on and so forth. We calculate A0 by averaging over, again, any t0 interval based on the information given here. Well, we know that t0 is pi. Based on the symmetry in the waveform here, there is none, but we're given the mathematical expression for x of t in the interval from 0 to pi. So that's going to be the most convenient integration interval from 0 to pi. And in that interval, I'm given that x of t is e to the minus t over 2 dt. So I'll leave the details of that integration to you, but it turns out to be 2 over pi 1 minus e to the minus pi over 2, which has a decimal approximation of 0.5043 for the average value of x of t. So if x of t were actually a voltage waveform, and we measured the voltage with a DC voltmeter, we'd measure about half a volt. The a of n coefficients are 2 over t0, so there's a factor of 2 here. Most convenient integration interval is going to be 0 to pi. In that interval, x of t is e to the minus t over 2. And then for the a0 coefficients, we're integrating the product of x of t and the cosine, and the frequencies here are n omega 0, so 2n t, and then we're integrating over t. And again, you can look this up in a table of handbooks. It'll actually turn out to be this term, so I'm going to just abbreviate that as a0, 2 over 1 plus 16 times n squared for my an coefficients. There's one thing to notice here is that as n increases, my a of n terms get smaller and smaller. So which means that the amplitudes of those corresponding sinusoidal components are going to get smaller and smaller and contribute less and less to x of t at the higher harmonic frequencies, because they will have smaller amplitudes. Similarly, Bn is 2 over pi, integral from 0 to pi, e to the minus t over 2, but now sine of n omega 0, or 2nt dt, and this turns out to be a0 8n over 1 plus 16n squared. And we see also for the Bn that they become smaller and smaller as n increases. They don't decrease quite as rapidly as the an coefficients. The an coefficients go towards 0 as n squared. The Bn coefficients will actually go towards 0 with increasing n as 1 over n. So finally, we can express x of t like this. It's the a0 term, which actually appears in all of my ANs and BNs, so I'm just going to factor that out. Of course, as the decimal approximation, that's equal to the 0.5043, and then I'll have 1. Actually having a little trouble with my pen here, so let me try and do this with the mouse. 1 plus the sum n equal 1 to infinity. So you'll have to bear with me. 1 plus 16 n squared times the cosine of 2nt and then plus I'm going to write it this way. I'll factor out the 1 plus 16n squared, and then that'll leave me with, here I have an additional 4n term for my sine component. 2nt. I'm going to stop right here, and we'll continue this lecture as soon as I get the problems with my pen straightened out. Okay, let's continue that example. I think I've got the problems with my pen corrected. So using those values we had for A0, we know that C0 is equal to A0, and the decimal approximation for that is 0.543. My Cn coefficients in the compact Fourier series representation are an squared plus bn squared, or it turns out to be in C0 times 2 over the square root of 1 plus 16n squared, and the theta n coefficients are the inverse tangent of bn over an. You get some cancellations there of that term that's in the that common term that's in the denominator. So this just becomes the inverse tangent of minus 4n, or because of the odd symmetry of the inverse tangent function, this is minus inverse tangent of 4n. Okay. So an alternate expression for x of t would be my C0 term, so 0.5043 times 1 plus the sum from n equal 1 to infinity of, got my amplitude coefficients, 2 over 1 plus 16n squared, and then cosine of 2nt, and then plus my phase terms, which are minus inverse tangent of 4 over n. Now, in order to plot these, probably the first thing I want to do is actually make a little table of n, Cn, and theta n. I know for n equals 0, that's my C0 coefficient, for my average value. That's just this constant term here, so there's no corresponding phase angle. For n equal to 1, I evaluate the amplitude with n equal to 1. I'm going to get 2 over the square root of 17 times the 0.5043. That turns out to be 0.244. And then the phase angle with n equal to 1 is the negative of the inverse tangent of 4. That turns out to be minus 75.96 degrees. by convention, we plot the phase spectra in degrees instead of radians. N equal 2, 0.125, corresponding phase angle, minus 82.87. For n equal to 3, amplitude term of 0.084. Again, these amplitude terms will continue to get smaller and smaller as n increases. For our phase angle term, as n increases, as this gets larger and larger, the inverse tangent will approach 90. We've got the negative inverse tangent, so as n increases, our phase angles are going to approach actually 90 degrees. Okay. So here's the table of these coefficients and also the corresponding phase angles. So with the amplitude spectra, it's probably easiest to plot these versus n, but we also are interested in the frequency, the corresponding frequency components. So for n equal to 0, that's a frequency of 0. We plot our C0 component. Of course, that's going to be right here at approximately 0.5043. And then our fundamental component, which in this case has a frequency of, remember, omega 0 is 2 radians per second. It has an amplitude of 0.244, which is slightly less than half of A0, so I'll draw that. At n equal to 2, corresponding frequency of 4 radians per second. Looks like we've gone down by about another factor of half. So 6 radians per second. Again, these are continuing to decrease. And theoretically, they never get to 0, but they do get smaller and smaller. The phase spectrum. So this is a plot of my Cn versus frequency. So this tells me the amplitudes. I can read off the amplitudes from this graph of each of the frequency components that make up x of t, and similarly from the phase spectra. This is a graph of theta n at n equal to 0, it's 0. Again, I'll have n and omega just as above, so I'll just line these up. They're approaching negative 90 degrees. I'll show that here, and then the first one is at minus 75.96, and then minus 82.87, minus 85.24. So these phase angles are getting closer and closer to 90 degrees for increasing values of n. So this is a plot of the amplitude and phase spectra for this particular periodic waveform.